Good day from Chem Help ASAP. This is a reaction video. I'm reacting to a video put up by Extractions&Ire. Now the particular video I'm reacting to is actually two separate reactions. On the first end, he makes cyclopentanone. And I've already done a reaction to a previous cyclopentanone video from Extractions&Ire. So I'm actually looking at the second half of the video, which is making a ketal from cyclopentanone. So we're just looking at the second half of the video. This reaction is such a fundamental reaction in organic chemistry. Everybody who takes organic chemistry learns about this reaction probably in their second semester of organic chemistry. So I'm kind of excited about this video. Throw in the fact that Extractions&Ire has some birds in this. I mean, it's got all kinds of action. So I'm looking forward to this video and I hope you enjoy it. Okay, I have to start with some mute because he has some montages going on and he has music overlays that'll, I think will give me a copyright warning. So let's start. He is pouring toluene. The bulk of what's in that flask is toluene. That's going to be the reaction solvent. And with a pipette, he's adding some sulfuric acid. So let's see, he'll show that. There's a bottle of sulfuric acid, and he's just using drain cleaner. And this is why sometimes people say, don't use drain cleaner on your house with its metal pipes, its copper pipes, because the drain cleaner will do a number on your pipes. So anyway, this is the source of sulfuric acid, and he's using this. Now, he is pre-mixing his acid, his sulfuric acid and toluene to kind of get rid of some impurities that it might form. We're going to see that here in a second. So he's swirling that around. He's heating this up. Again, we're on mute to cover up the music. And you can see he's getting some discoloration and he's forming some tars in this reaction. This is after 30 minutes of reflux. And note he has this setup to the right. So this has to the right, we have this tube, and there's some liquid in that tube. This is called a Dean-Stark trap. We'll go into more detail about the Dean-Stark trap when we start running the reaction. But I suspect he's doing two things here. One, and he explicitly states this, that he's trying to let some tars form in the toluene so he can get rid of those before he starts his reaction. And two, I think some of that drain cleaner, it might not be pure sulfuric acid. It might have some water in it. So this gives him a chance to remove some of the water from that sulfuric acid because the excess water, he wants to minimize that water in his reaction. All right, I edited a little clip out because he was finishing up his previous reaction making the cyclopentanone. Now he's coming back to this refluxing toluene sulfuric acid mixture. And I think we can turn on the volume again.
Mixture. Now, concerns that the toluene would tar up if we just added sulfuric acid and reflux it. If it was like kind of technical grade sulfuric acid, oh my God, I can feel my skin literally on fire. It is.
He makes comments throughout the video. It is blazing hot when he did this video in Australia, and he is getting cooked in the sun.
Fuck me. It's hazardous being out here. Sorry, I'll just get through this. Look, this might be controversial, but I don't think this is too bad. It's a little tarry, but nowhere near as bad as what it could be. There is some tar around the sides, and there's a little blob of tar that's definitely condensed at the bottom there. You can.
I am surprised he sees this tar. Of course, I don't typically treat toluene and cook it up with sulfuric acid every day, so I don't know. But this apparently is something he expected. And how do you know he expected it? Because he went through this process before he ran his reaction. So he knew this was going to happen. This is not a surprise to him. But he is forming some kind of polymeric material. That's that tar that's forming. And so he just wanted to give that a chance to form before he ran his reaction.
See, it stuck the stir bar in. And some crystals. I'm pretty sure that might be toluene sulfonic acid now that this is all.
So toluene sulfonic acid, you can form toluene sulfonic acid by heating toluene with sulfuric acid, which is exactly what he did. He just did an electrophilic aromatic substitution. So this is completely chemically reasonable, but I would not have expected it.
Or cooled down. So basically, I'm not going to redistill the toluene. It looks fine. I mean, it looks okay. I wouldn't say fine. but it's not as bad as it could be. What I'm just going to do is I'm going to decant it into a different flask so that we leave this tar ball behind and this tar on the side, and then we'll use this toluene and sulfuric acid mix as is.
So when he decants that liquid out, yes, some of the color will come, but all that residue on the flask, that'll be left behind. So he's just getting rid of some of that preformed tar so it doesn't contaminate his subsequent reaction.
Well, that wind is nice. Oh, sorry. Oh, that was Dad. I even pissed Dad off. So did
that was the first appearance of the bird. He'll refer to them regularly through this.
Did you father all of those children or just some of them?
Oops, I paused. Let's go.
The ethylene glycol coolant introduced at the start. It's pretty much mostly ethylene glycol, 1,064 grams per litre, which is close-ish to its density. So there's just a little bit of water in there as well.
So that's his source of one of his reagents, ethylene glycol. He made cyclopentanone in a previous reaction, so that's his other key reagent. Now notice, that is green. I wouldn't want to add that to a reaction. What's he going to do about that?
Not quite anhydrous ethylene glycol, but here's some I distilled earlier.
Oh, okay. So he saw the same thing. I don't want to add that green stuff to my reaction. So he distilled it to get a more pure form, maybe a little less water. And so when he distilled it, colored impurities tend to be very high boiling, so you can separate based on their boiling point. And he got his ethylene glycol, and he has some nice looking ethylene glycol to use in his reaction.
A little bit in this bottle, little shitty plastic bottle, but it's beautiful, dry stuff. So I'm sure there's enough there. Well, I don't know. Maybe that'll be our limiting reagent, but it should be enough to do quite a large scale reaction here. We've got our cyclopentanone. It's been sitting in the sun.
So that's the material he just made in the first half of the video, to which I'm not reacting right now.
Could move that out. Ethylene glycol, and we got our toluene and our sulfuric acid mix, which has kind of been pre-tarred, let's say. Pre-tarred? I know, maybe that's not a good word. It sounded better in my head. All right. On that note, let's pack this shit up and then set up some new shit.
Okay, so here comes the music. I'm going to cut off the music, so we're going to go in silence for a little bit. I'll just voice over. So he has 178 grams of ethylene glycol. Good. 190 grams of cyclopentanone. I'm sorry I'm covering that up. And about 300 milliliters of this toluene and sulfuric acid mixture. And that's everything together. So I'm going to pause and just show the reaction. So this reaction, on the left, we have our two starting materials. We have cyclopentanone, that's a ketone, that's the key functional group that's going to react. We have ethylene glycol. Ethylene glycol is an alcohol. This molecule actually contains two alcohols. This is what people use in antifreeze. So that's our alcohol, our diol. We're going to react these in the presence of a catalyst, and that's the acid that's in the toluene. I haven't put the solvent in here, but toluene is a solvent. That's the medium in which these chemicals are mixing together. And then our product will be this ketal, and then will also form water. So this is a reaction. This is, again, a classic reaction. A lot of chemistry is built on this reaction. Even though the chemistry might look different, it's still at its heart, it's essentially this reaction. So as it stands now, he's mixed everything together. As it turns out, the ethylene glycol is too polar and doesn't mix well with the toluene solvent. So he's kind of getting a biphasic mixture, but he's going to heat the dickens out of this. And he's going to force all this to interact and react. And so that separation is not a problem at all. Okay, so he's heating this up. He's got some gunk in his condenser lines. No surprise. That happens sometimes. And he's heating it. Something's boiling. It's a little shaky camera here, kind of Blair Witch Project. And he's heating stuff. I'm going to let this go. In a second, I'm going to pause it. And let this go. Okay, so he's draining some liquid out the bottom. That's weird. Let's get a nice view of the setup. There's the bird again. Hello, Mr. Bird. Okay, that's a good setup. Now let's look at this. This reaction, and let's put it back on the screen. This reaction has a problem. it's not energetically very favorable. So if you look at, sometimes when you talk about the energetics of a reaction, you'll simply look at what bonds are broken, that takes energy to come in, and what bonds are made, and that releases energy. And you calculate the energies of your bonds. Well, if you look, to do this reaction, we're going to have to break 2 carbon-oxygen bonds, and that's to the oxygen in the ketone. And we're going to have to break 2 OH bonds. Those are in the starting alcohol, the ethylene glycol. And in the end, we're going to make 2 CO bonds, and those are in the ketal. And we're going to make 2 OH bonds, and those are in the water. Well, the net effect of that is 0. So if we're making 2 CO bonds and breaking 2 CO bonds, that's a wash. Same thing for 2 OH bonds. We make them and break them. That's a wash. So energetically, this is not a very favorable reaction. So we have to do something to this reaction. And what we're going to do is we're going to remove one of the products of the reaction. So this reaction will establish an equilibrium. And we'll get about equal amounts of everything because there's no energetic difference, meaningful difference between the starting materials and the products. But as we form water, if we can have a trick to remove the water, then that will cause the reaction to drive to the right and form more products. And of course, as we form more water as a product, we will remove it and the reaction will continue to be driven to the right through its equilibrium. This is an idea called Le Chatelier's principle. We are perturbing the equilibrium to drive the reaction one direction or another. In this case, we're driving it to the right. We're driving it towards the products. How do we remove the water? Well, that's where this image on the screen is important. This is called a Dean-Stark trap. To the bottom right, we have a reaction flask. We heat up the reaction, heat it to boiling. The toluene boils and the vapors rise, and as we form water, the toluene and water will actually boil together and form something called an azeotrope. It rises up the glassware and then travels over that arm to the left, hits that cold condenser, and at that point we now have liquid toluene and liquid water. They are not miscible. Water is more dense than toluene, and water will sink to the bottom of that graduated region on the left-hand side of the screen. And as it sinks, we'll form a separate layer of water, and you can drain that water out the stopcock in the bottom. And any toluene that gets collected will just kind of dribble over and overflow back into the flask. So we're continuously leaching out the water, collecting it, draining it off, and running this reaction. So we're implementing Le Chatelier's principle, which is one of the fundamental ideas of chemistry. So here, let's watch this go. So he's heating, he's draining off liquid as it goes, draining off water as he collects it, boil some more. Oh, and I think we can we play audio here? Let's find out.
Tough being a little bit, isn't it?
Just a bit. There's a birdie. No, when I was in lab, we used to have animals, but they're always cockroaches. So it's pretty cool. He actually has birds in where he's doing his chemistry. Okay, this still has some music going. He's monitoring the temperature. Okay, now I think we can listen.
Hours, 5 hours yesterday, 7 hours today. I didn't really run it overnight too much. In fact, I kind of left it standing overnight, which kind of made it go black, I think. Well, I might have gone black anyway. I mean, play the clip. It's tarry. It's not a great sign, but maybe just what happens. Maybe. Definitely.
Anytime you heat reactions, you're going to get some discoloration. This is not a surprise. I'm not saying you should be excited about it, and he's clearly not excited about it, but it happens. You just got to run with it.
I think running this with toluene rather than benzene, you can use benzene for this as a solvent, which boils at a lower temperature, chars it and tars it a lot less than toluene, which kind of, this reflux is at 110, 120 degrees. Do people know how this works? I probably don't need to explain this. I mean, there are a lot of people, shout out to all the people who have no idea what I'm doing, but just enjoy watching me do things. People comment that quite a bit, which is fantastic. Shout out to you guys. But in short, yeah, the toluene boils with water, it carries over. The water is actually technically an azeotrope, but it carries it all up and then separates into 2 immiscible liquids, and the water floats.
So let me go back just a bit. He's talking about this separation process a little more. Note that See how clear that toluene is at the top of the trap side of this distillation apparatus? That's a good sign. Once everything is clear, that shows that there's really almost no water being formed. And if there's no water being formed, then the reaction's probably done its thing. And he says he let this go about 12 hours. So everything ought to be done. Visually, it looks like it's done. This is just visual confirmation of what he suspects already.
Floats down here, and then we tap it off. And the toluene at the top here just floats back. Any water that's created in this reaction, we instantly kind of drive off and collect, and that drives the reaction forward because we're continually sucking water out of that reaction. So
continuously sucking water out and driving the reaction to completion by Le Chatelier's principle. If there's nothing else you remember from this, Le Chatelier's principle. It's just a fundamental idea in chemistry.
We have here about 60 mils, actually I just measured it, 61 mils of water, which we've basically extracted from this reaction, and it tells us that our reaction is progressing. We expect about 80 mils. There was some extra water, but I was just chucking it away before.
Okay, I want to pause here. He talks about the amount of water. How does he know how much water? Well, let's put this on the screen. So he knows that he started with 190 grams of his cyclopentanone, his ketone, and he had 178 grams of ethylene glycol. Well, if you go through the math, the molecular weights, how many moles are those? As it turns out, he has 2.26 moles of his cyclopentanone and about 2.87 moles of his ethylene glycol. So he has more moles of ethylene glycol than cyclopentanone. They react in a 1-to-1 ratio. That's the stoichiometry of the reaction. And so he knows that the cyclopentanone is the limiting reagent. If he has 2.26 moles of ketone, then in theory, he can make 2.26 moles of each product, one being the ketal and one being the water. So if you go to the right-hand side of the equation, if we form 2.26 moles of the ketal, then that would be ultimately, if you go through the molecular weight, 289 grams of the ketal. And if you go through the molecular weight with water, 2.26 moles of water is about 40.7 milliliters of water using the density. So he said he expected 80. By my calculations, I get 40. He saw 60. He's going to talk about maybe having a water leak later. But, he's gotten a lot of water off. So if you carefully monitor how much water you form, you can actually monitor the progress of the reaction based on the theoretical amount of water you can form in this reaction. So the Dean-Stark trap gives you a method to actually monitor your reaction, which is pretty cool.
I remembered that it's a good idea to collect it so we can actually keep track of the reaction. So yeah, I reckon we'd be close to the end point. Basically, I'm giving up now because it's stopping, right? Like it's taken maybe half an hour to get to a mil or something like that. So there's not a lot more water coming over. At the start, there were drops of water.
Look how clear that toluene is. There's no water in there. He's right. This is done. No more water forming, no more reaction progress. Time to stop it.
Quite often, but now, sorry, it's quite hot. I got to stop touching that. Yeah, you can see one tiny droplet. So, we could keep going forever and there'd probably still be little drops of water, but yeah, very, very few drops of water coming over now. Yeah, we're stopping it, but actually we really want to remove a lot of the toluene anyway. So I'm just going to keep this going and take off the toluene that distills over because we're going to have to do the vacuum distillation step. Hello, yeah, greetings, you can come through. Sorry, she's here every 10 minutes. It's fine. As soon as I leave, she'll come and feed the guys, but it's all right. Shout out to all those people that are watching.
Again, I'm used to having cockroaches in the lab, so it's pretty cool to have birds.
In this video just for the bird content and hate when I talk about the chemistry. There's at least one of you, probably. What we don't want is, I suppose we don't really want to sit this reaction around just like I've done in the acidic mixture because we're forming a ketal, which we formed by driving off the water. But if it's still acidic, which is quite acidic, we've got sulfuric acid in there, that sulfuric acid can really attack the ketal and break it apart. So once we've taken off quite a bit of toluene, we'll neutralize it. Then we really just want to go through a washing step to try and remove any leftover ethylene glycol, any leftover cyclopentanone.
Okay, so just a little recap. He has that's his flask. His flask contains his product. It also contains a solvent and still contains that acid catalyst. He didn't want to cook it indefinitely in acid. So if the reaction's done, let's get this to stop. So he needs to remove that toluene. He'll remove that through allowing the toluene to continue to boil over, and he'll collect that toluene. So that'll get rid of the toluene. He'll have to take care of his acid. He'll have to neutralize that acid. And then he'll be able to address his product, which is in the dark material in that flask.
Both of those dissolve in water, but our end product doesn't. Maybe we'll remove some of the tar, we probably won't. And then we'll set up this vacuum distillation. Just because once again, I'm not very confident about my vacuum distillation. So if we have a whole heap of mixtures, theoretically we could just put it through a column and carefully distill our product and chuck away everything that we don't want. But doing a washing step before then lets us kind of remove a lot of the stuff that we don't care about, which is...
Okay, remove a lot of stuff. Remember, and I'll put it back on the screen, when we look at stoichiometry, he has an excess amount of ethylene glycol, more moles of ethylene glycol than his ketone. So once the reaction's done, he should still have more ethylene glycol around. And so he wants to get rid of that. We know ethylene glycol is very water soluble. And so he's going to do a water wash, a water extraction to get rid of that excess ethylene glycol. And then hopefully he'll just have his product to purify.
Leftover ethylene glycol and cyclopentanone, so we don't have to really worry about that so much with the distillation. There's probably just going to be some residual toluene and our end product. And the toluene will boil a lot earlier than our end product will, so they should be easy to separate.
I want you to notice how much he's thinking about what's going to happen. Because there's a lot of things that could happen, and he's trying to anticipate all those contingencies and thinking, what action can I take now to minimize the problems down the road? If when you do experimental work, whether it's experimental chemistry or experimental physics, you're constantly thinking about how can I save myself problems down the road? Because sometimes problems down the road are really hard to fix. So maybe a little caution up front can, an ounce of prevention is better than a pound of cure. So he's just thinking through things and anticipating problems.
It's very black. It's very black, but we got quite a bit of water, so it implies there's at least some reaction going on. We just have to be optimistic. The only other alternative is just to abandon this and go live in the woods, you know what I mean? You just have to persist, despite the horrors.
Persist. It's hard to persist, but he's just going to grind through this.
Yeah, come through. Persist despite the horrors. No. Persist despite the horror. I'll turn this off. Thanks, fan. Doing a great job. We've removed all this toluene. Here we go. It's 300 mils or so, which is about as much as we put in. So I think there's a little bit left, but not too much. We're just left with a black liquid in the flask. It's not particularly thick. Yeah, we removed, that's the water with a little fly in it, sure, and the toluene. So I'm just going to neutralize the sulfuric acid. So we're just going to add in a small amount of
Okay, he still has his acid in there. He needs to get rid of that acid. As long as the acid is present, this reaction can continue. And so there comes a point in a reaction where you want to stop it. So he is going to quench this reaction. He's going to quench the reactivity of the acid by adding some base that will neutralize that acid. And then any reactions will be completely stopped. And then he can manage getting his pure material out of there. But this is, some people call this a quench. It's a little strong of a term maybe, but he's stopping this reaction by neutralizing the acid catalyst.
Sodium carbonate. When it's cool, which is now, I guess. Yeah.
Okay, I got to make this mute so we don't hear that music. He's adding a little bit of sodium carbonate to this. That's a weak base that'll neutralize the acid. Good.
Drips of water into the reaction mix just now. I thought that was pretty weird. I thought, where was that water coming from? It is the cooling water. You can see that green colour? See, it's why you dye your cooling water. Once again, this is not lead, but we can see the green colour of the cooling water. That's a bit of a shame. I like this condenser. Oh, I'll have to go in there. It's just that end there. See the glass seam is it's just leaking through a little bit of water. It's crazy. So I don't think it leaks when it's upright. Well, that's a bit of a shame.
I did calculate that he should have gotten less water than he got. So it could be that over the 12 hours of this reaction, it was leaking just a small amount. And that accounts for some of the water difference. I could have messed up the calculation, but anyway, there is a potential reasonable explanation for excess water now because he's identified a leak in his glassware. And that happens. That happens around these joints. This glassware doesn't last forever.
Anyway, I don't think it's ruined anything. Just hopefully, maybe those drips of water just near the end of the reaction when we're neutralizing it help neutralize it anyway. Should be all right. As long as it's neutral and there's a little bit of water, I don't think it'll break down the thing we've made.
A baby bird, not a cockroach, a baby bird.
He's not dead, I swear. They just do sit like that sometimes.
Okay, we need to silence that. Okay, here we go. So he's adding some water. Remember the purpose of that water is to dissolve the excess ethylene glycol. He's adding some salt to help give a phase separation between the polar and nonpolar layers. The polar layer will be the water layer, presumably containing ethylene glycol. The nonpolar layer will be less dense. It'll float on top. That will be where his organic product is. Mixing it all up, putting it in a sep funnel that allows them to separate out the layers. You can see that bottom layer is a little bit clearer, a little bit lighter color. That's the aqueous layer, and he's going to drain that off to get rid of the water layer. And that should get rid of any excess ethylene glycol. Okay, he's going to dump it all back in a flask. And boom, I think...
All right, we have arrived at the vacuum distillation. So we have our mixture here. We've obviously washed it. It's just, hopefully, mostly the ketal, which is what we want. But we have to do the vacuum distillation. It's probably one of the more technical things we have to do in this whole series. I'm really not set up for it and haven't done one in a while. Last time we ran it and we got it working, we used this pump here, which is a good pump, but not really what should be used for this kind of thing. And we ran the vacuum through this to use as a vacuum gauge just because that's kind of what I had on hand. But this time, we're going to do the same thing. It worked. I don't know. I got slightly better tubing. I bought some MPT fittings and some of them have arrived. I had a better gauge, but I don't have the adapters for it. They didn't arrive. I still want to do the science, so we're just going to be running it through this again. Maybe a slightly better cold trap, better tubing, and we'll see how we go. There's not as much as I would have liked. We're trying to do this on the largest scale we possibly can.
Now remember, by my math, he would expect 289 grams of product. And if that's a 1 liter flask, I think he has every bit of 289 grams. Maybe there's a little bit of ethylene glycol in there still. Maybe there's a little toluene. But I think that looks like that's a lot of material. I think he's in good shape by my eye. Now, he's doing a vacuum distillation. Why do you do a vacuum distillation? Well, he wants to distill his product, but his product has a high enough molecular weight that to boil it, it might thermally destroy his product. So by reducing the pressure over the reaction, his product will boil at a lower temperature, maybe at a lower temperature at which it will not be destroyed by the heat. So by lowering the pressure, pulling a vacuum over your material, you reduce boiling points and you put less thermal stress on your compounds. And he wants his compound to survive, so less thermal stress is good.
And already it seems like there's not heaps there. Still quite a bit, but not as much as I would have liked. Yeah, there's a lot to set up here. I don't know, will this tubing be good? Hopefully this tubing will be good. Got my lifetime supply of high vacuum grease here.
That is true. That is a massive amount of grease, but for some reason when you get grease in labs, vacuum grease, they always give you these big tubes. You will never in a lifetime use that much grease, but they give you these massive tubes. It's cheap stuff, but it is a big tube.
Yeah. Hopefully the vacuum pump goes okay. Yeah, let's just try and run this vacuum distillation.
Okay, little montage. We'll mute this. He's putting everything together. Note that you can't have air leaks. So he's putting grease on the joints to make sure that they leak as little air as possible into the system. It's a distillation, so he's going to have a condenser. And he's turning on his big vacuum pump. That is a big boy vacuum pump. and he's pulling a vacuum. Everything is hopefully sealed tight. His tubing is airtight, doesn't let any leaks in, and he's running it. So now the flask on the left ought to start boiling, and he'll see bubbles. There are the bubbles, and that vapor will rise. Look, he's seeing it. Now this is he probably has a little leftover toluene. That's okay. He'll collect that toluene in his receiver flask. He's monitoring the temperature as he should. Collecting the liquid. You can see it on the right. Now he feels he's done with the toluene, so he'll swap out receiver flasks. And now, and again, using a little grease to make sure everything gets sealed. Now, presumably, this is product. You can see it boiling through that distillation column, collecting there. You often put a trap that will help prevent any vapors, unwanted vapors, to get pulled into your vacuum pump. That protects your pump. He's watching stuff, looking good, looking good. That's beautiful, clear, colorless product that he's collecting. Leaves the colored materials tend to be higher boiling, so you normally can separate the colored material from your desired product. Okay, he's going. That looks great. Beautiful. Okay, well, let's stop.
And after all this, we're left with 132 grams of very good quality cyclopentanone.
Okay, he got 132 grams. Remember, I calculated 289 grams, and that's a 40-some% yield based on my calculation. Now, let me go backwards so we can... Do you see that structure on his label is incorrect? I think he knows it's incorrect. I think he just drew it that way because he ran out of space. But anyway, there are 2 more carbons in there. But that's the product, and it looks great. A nice, clear, colorless liquid.
Pentanone ketal, which is, it's great. 132 grams is a lot more than we got previously. When we did this run before, we got about 44 grams, of which we have about...
So note he's holding that bottle. Let's move it around. Note he has a full second 5-membered ring, so he knows what the structure is. He just has a structure off on that one label.
About 20 grams or so left. So 132 grams is a lot more. And our yields overall were better too. We got a 46% yield this time, whereas the last time we only really got a 32% yield. But I'm still a little bit disappointed.
Listen, organic chemists are never satisfied with the yield. Look, he's doing this reaction in a shed that is also an aviary for birds. Okay, and he got a 46% yield of this ketal, which required careful exclusion of water, and maybe had a leaky piece of glassware while he was doing it. So this is a phenomenal result in my eyes. But organic chemists, we're full of doubt, and we worry about stuff. So he's just playing the role of an organic chemist here.
132 grams is less than I hoped we end up with on this large-scale run. Really, I think not being able to run the Dean Stark in the 2-litre flask is really what held us back the most, because look at all this cyclopentanone we didn't end up using. I was really hoping for at least 200 grams. But really, I think the surprising thing is our low yield once again. 46% is not particularly very good. And here's this tar left over from the vacuum distillation. Whoa. That is high quality tar. I'm nearly lost for words at that tar. That's amazing. So yeah, we've definitely lost some yields in there, and maybe our vacuum distillation wasn't so great really either. You could tell there was definitely some bits of product.
Oh my goodness. I would be doing if I could do a backflip, I'd be doing backflips. I think that's a great result. He's just, he just wishing he got more. Every organic chemist wishes they got more.
Getting caught in the lines and in our cold trap at the end. And even this first fraction definitely contains quite a bit of toluene, but probably also contains quite a bit of product that we've kind of have to throw away. Well, I could try and boil the toluene out of it, but for the sake of purity, we're kind of left here with our 46% yield. If we combine it with our other fraction here, well, not our other fraction, our previous synthesized stuff from September 2020, together we have about 150 grams, which is quite a bit to go on with, because we want to convert all this into the tribromo, which is the next step. We need 600 grams or so of bromine, which is...
I'm totally going to react to this tribromo reaction. This is cool chemistry. Absolutely.
Already quite a bit, but I would have liked a little bit more. I definitely didn't really want to have to do this ever again. You know, I'm always hitting it with these low yields, actually. Speaking of which, how are you guys going?
There's two really healthy guys, and the third one has gone missing. So I suppose that's how it is in the bird world.
My yield for birds is even only at 66%. So it's a lot.
I would round that to 67, but you know, that's fair, 66.
Oh, you would kind of season. Well, on that note, well, that's a very dark note to end on. Oh my God. Yeah, shit. On that strange note, I will see you next time for more chemistry. Bromination step next, and then really it's the UV step we've got to start to worry about, and maybe even start thinking about some cleanup, because this is even half of the dirty glassware we've made for this video. Anyway, thanks so much for watching. I'll see you for some more bloody chemistry soon.
Hey, that was great. Let's go back. Let's get him back on the screen. There we go. Thank you, Extractions&Ire, for sharing this with the chemistry community. And you who are watching, thank you for your attention and watching this reaction video. If you have any comments or questions, please leave them in the video description. Anyway, take care.